Welcome back. In this part of the tutorial, we are actually going to start and create our Segwit addresses. Now, the first thing that we need to do is to decide what type of address we want to create, because as we saw earlier, there are two types of Segwit addresses. One which is the native Segwit address, and the other one which is a nested or backward compatible Segwit address. Luckily, as we can see in this flowchart that I've made over here, the steps that are required in order to generate those two types of addresses are very similar, and in fact, creating a backward compatible and nested Segwit address, this is just an extension of the process that is required in order to generate the native Segwit address. There are few minor differences that we will see later how they come into play, but in a general, as a rule of thumb, creating a nested, a backward compatible Segwit address will take us through almost all of the steps that are required in order to generate the native Segwit address, plus some other extra steps that are required to nest this address, this native address, inside of some script hash that older clients can also use. Now, just to get some clear idea on how those differences come into play, we can have a look at a modern blockchain explorer. For example, I am using right now blockstream.info, and I can see in the list of the transactions that I present here both type of Segwit transactions, which of course stems from the different type of Segwit addresses. And I'm going to completely randomly choose two transactions. Each one uses different address type. The one on the left is the native Segwit address, and the one on the right, this is the backward compatible nested Segwit address. And immediately we can see that there are three major differences between those two types of addresses. First, we can see this type field right over here, which is quite self-explanatory. The one on the left side, it is the native Segwit address. Therefore, it is come from the type pay to witness public key hash. The one on the right, this is the backward compatible Segwit address, which at the end of the day acts or behave very similar to the old-fashioned pay to script hash type of transactions. Inside of the script hash of this transaction, we will find our Segwit component. The second difference that is very clear is the encoding. We can see that the native Segwit address begins with BC1. It has a different length and a different car set, which basically represents a different type of encoding. This encoding is known as the batch 32, and it was introduced alongside the Segwit soft fork almost 2 years ago. On the right side, we have the old encoding scheme, the one that still uses base 58. This is the one that older Bitcoin clients supports and know how to interpret, which of course, this is what we want to achieve. We want this type of address to be backward compatible, so we are placing it or representing it with the proper encoding, with the proper base 58 encoding. Now, the third and final type of difference that we can see between those two addresses comes from this script public key field right here. This difference is actually perhaps the most important difference between those two types of addresses, because at the end of the day, the address itself is not the information that appears on the blockchain. When I generate a Bitcoin transaction and publish it onto the blockchain, I don't specify the recipient address on the blockchain. Instead, I specify some sort of a specific type of a script. The address helps me to convey this script in a more human readable format. However, the address itself, by itself, this is not the information that appears on the blockchain. The real heart of the transaction is this field right over here. And we will later see what this field actually means. We will start to talk about it a little bit in this tutorial on addresses and in more details when we will actually deal with the transactions itself. But it is very important to remember that the information that actually stays on the blockchain, it's not the address, it is this script public key right over here. This is the field that actually appears on the blockchain. And the address at its core is just a way to convey information about this field between the sender and the recipient. Okay, so now that we saw the differences between those two types of transactions, this is time to actually start finally working on our code. And I'm going back to this flowchart right over here. And I'm going to see that the first step is to generate some sort of a random number. And we are going to store this number as the private key. This random number is supposed to be 256 bits long or 32 bytes. And I will generate this random number using Python's built-in random library. So I'm going to import this library and I'm going to generate it using the random getRandBit method. I need to make sure that it will be 256 bits. And I'm going to store these 256 bits in its binary form as my private key. This changing from hexadecimal and or encoded representation into its binary form, this is something that I will do quite often in those video tutorials, because at the end of the day, it will be easier for me to display the information either encoded in hexadecimal, batch 32, base 58, and so on. But it will be easier to work on this information while it is in its binary form. So this is why I will often convert the information back to bytes using the 2 bytes command. And the sooner that you will get used to work with these byte conversions, the better. Okay, so this random 32 bytes long, 256 bits long number, this is basically our private key. And yes, this is the number that controls your Bitcoin. Whoever gets control over this number can basically claim all of the Bitcoins that are stored in the addresses which are derived from this private key. However, in order to actually use this number, we need to attach it to some sort of a mathematical entity, because this random number by itself, there isn't much we can do with it. I mean, just imagine that you get the number 1 billion. You can't really use this number 1 billion. It doesn't do anything by itself. It needs to be used in conjunction to some sort of mathematical algorithm. You need to actually use it in some sort of an equation, in some sort of a graph. You need to manipulate this number to make sense out of it. So the mathematical graph that we are going to use is of the type SECP 256K1. And this is basically a type of elliptic curve. The requirement to attach this number into this elliptic curve, and the way to do so is something that is explained in details in the mathematical documentation of what is known as the SECP 256K1 technical documentation that deals with the mathematical equations that are reused for this elliptic curve. Luckily for us, Python already provides us with some sort of library or a package that contain all of those mathematical primitives and functions, and we can just import this library. This is known as the Ecdsa library or Ecdsa package, which stands for elliptic curve digital signature algorithm. And we are just going to import this package, and we are going to use the package method sign-in key from string. We are going to give it our private key, our random number, which is represented in its binary form. And we are going to ask it to attach this private key into a specific type of curve, the Ecdsa dot secp 256 K1. So let's just have a very quick look. We can see that we generated some sort of a random number. We stored this random number in its binary form, and we called it our private key. But our private key by itself doesn't mean much. We have to actually place it on some sort of a curve, on some sort of a mathematical entity. And we are using the Ecdsa library in order to take our private key and place it onto the secpk 256 K1, sorry, the secp 256 K1 curve. And this basically creates a new entity, which is known as the sign-in key. We made this slightly artificial distinction between the private key and the sign-in key because while the private key is the magic number that will allow people to claim our bitcoins, by itself it won't do much. We still need to use it with some sort of a mathematical entity. So we created another type of variable, which is known as the sign-in key, that contains both this magic number, the private key, and this mathematical entity, the curve. And this object, this is the one that we will actually use to create our public key and later to sign and verify transactions or other type of messages. Okay, so now that we have our sign-in key, it is time to go to the next step, which is to convert our sign-in key using the mathematical magic of our Ecdsa library, of our elliptic curve, into a verification key. And the way to do so is very simple. We are just going to take our sign-in key object and use the method getVerifyingKey. This method getVerifyingKey comes from the Ecdsa package, so it is very easy to convert from the sign-in key to the verification key. The verification key by itself is a 64-byte long number. This number represents some sort of a point on our elliptic curve graph. This point is represented, like many other points in mathematics, using its coordinates, is x and y coordinate. So the first 32 bytes of these points represents the x coordinate, and the last 32 bytes represents the y coordinate. Now, in the past, it was possible to take this point as is and use it to generate our Bitcoin addresses. But the good developers of Bitcoin decided that using the entirety of this number, the entire 64 bytes number, the x and the y coordinate, is not the most efficient thing to do. I mean, if we already know the graph, and we do know the graph, it has been predefined as the secp 256k1, and the information about this graph and the function of this graph are already well defined. We can just take the x coordinate, which is only 32 bytes long, and use it as an input on our graph to get our y coordinate. In this way, we can save a lot of storage space on our blockchain, because when the time will come to actually spend the bitcoins that are stored in some address, I will be required to provide the public key that is associated with this address. And if I provide the entirety of the public key, I will need to provide 64 bytes. But instead, I can just provide 32 bytes for the x coordinate and ask the other participant to just calculate the y coordinate by itself. They already have the graph. And this way we can save up to 50% of the storage space that those public key used to take when they were published onto the blockchain. So this is basically brings us to our next step of creating the compressed public key. Again, it's a public key, but instead of supplying both the x and the y coordinates, we are just going to supply the x coordinate and expect the end user to calculate the y coordinate by themselves. Now, there is just one little caveat that needs to be taken into account when we are creating our compressed public key, and that is, if we have a look at the graph, the curve that we are about to use, we can see that it is a symmetrical graph. That means that for each x coordinate, there are two possible y coordinates. In this graph over here, we can see that there is either a plus y or a minus y. And for the real SECP256K1 graph, for that one, because they are using some sort of a vectorial field, I will not go into that in depth. But in that one, what differentiates those two y coordinates is that one is an even number and the second one is an odd number. So we need to give away the x coordinate plus some sort of a flag that tells us whether or not our y coordinate is odd or even. Luckily, it is very simple to check if a number is odd or even using Python. We are just going to use the modulus operator for that. So we will say that if our verification key, and we need to convert it back to integer, and this integer we are going to display it in a big endian byte order. And this might be a bit confusing to some of you, but this is just the way it has been defined. So big endian also as a signed integer. And once we got this number, we want to use the modulus operator by 2 and see if the remainder equals 0. If it does, that means that our y coordinate was even, and we are going to store our public key as the x coordinate with the prefix 0, 2. This prefix has been predefined in Bitcoin technical documentation, so we're just going to take this 0, 2 and attach it to our x coordinate as the prefix. If it is an odd number, instead of 0, 2, we will just attach as a prefix the number 0, 3. And this way, we got our compressed public key, which is simply the x coordinate of our verification key, plus a simple 1 byte long flag that tells us whether or not we are in the odd y or the even y coordinate. Okay, so now that we got our compressed public key, it is time to move to the next step, and we consider the next step is basically to take this compressed public key and hash it twice using two different types of hashing functions. Those two functions are defined in the Bitcoin's documentations, and they are SHA-256 and RIPE-MD 160. So the first thing that we need to do is to import our Hashlib package, and then we are going to generate the SHA-256 of our compressed public key using Hashlib SHA-256 public key, and then we need to create an object for the RIPE-MD hashing function. This is a bit of a weird step, but this is just how the package works. We need to generate a new object using the method hashlib.new, and we need to specify the type of the hashing function that we wish to use, which is of course RIPE-MD 160. And now we are going to take this object and we are going to update this object with the digested result of our SHA-256. So now when we digest our RIPE-MD 160 object, we basically received our key hash. Let's look at this again for a second. We have two hashing functions, two hashing objects, one SHA-256, the second one RIPE-MD 160. Both have been defined in the Bitcoin's protocol. This is how I know to choose those two specific ones. And I know that I need to start with the SHA-256. Again, this is the way it has been defined. And I need to take the result of this SHA function. I need to give it to the RIPE-MD hashing function as an input. And the output of this final hashing function, this is basically our key hash. This is basically the hash of our compressed public key. And this is the object that lies at the heart of the Segwit addresses, both the native and the nested addresses, the backward compatible address. And now that we got this key hash, we can choose one of the two following paths. One path will be just to encode this key hash using this new batch 32 encoding scheme, which will help us to create the native Segwit address. And the other one is to start nesting this key hash inside of scripts to generate the nested Segwit addresses, the backward compatible Segwit addresses. So the next two videos will deal exactly with those topics. One of them will deal with the nested script, how we can take our key hash and nest it inside of a Segwit script to get the backward compatible Segwit address. And another one which will simply show you how to encode this key hash that we just created into a native Segwit address. So I guess I will see you in one of the next two videos. You will choose which one you want to watch, or perhaps even both. And see you then.